All right, so last week we started part two, where we're talking about multiple servers, multiple systems interacting. And so we talked about replication, and that's where we're taking the same data and having multiple copies of it. So the challenge there is writes. So this week we're talking about partitioning, which is within each data set, each database, just splitting it up across multiple boxes, primarily for scalability reasons, right? And partitioning does not have nearly, whoops, too much. Sorry, hold on. Nearly the complexity that replication does, because with replication, you have multiple copies of the same thing. So when you have a write, you have to figure out how to get the write eventually to every copy. Partitioning, the whole idea is that you're splitting it up, and so each write amongst multiple partitions still only needs to go to one partition. Okay, and so what we'll see is that the problems are just much smaller here in partitioning. Now, as a note, partitioning is often used in conjunction with replication, and so all the issues of replication still apply to the replication portion of things, but the addition of partitioning, thankfully, isn't introducing a lot of new problems on top of the problems that you had with just the replication. So that's what this week's chapter is about. So there's a couple main topics in the chapter. The first one is, how do you decide how you're going to split things up? Okay, and there's a couple main ways. So the first thing you could do is, if you're looking things up by a key, and this could be documents, could be whatever, but just thinking of it abstractly as just key value, you split up the key into ranges. And if you have continuous ranges, then the nice thing is, if you did want to do some type of range query, if you wanted to know, people's last names between whatever, Smith and Thomas, then they're all kind of there, on the same partition, right? But the challenge with this is that it's hard to know a priori how to evenly split the keys amongst a different number of partitions. So you can do manual or you can do automatic on the boundaries, but it does have the benefit that, in addition to having continuous ranges on the same partition, not only that, but within the partition, the technology you use, you can actually store the data in sorted order. So conceptually, there's some benefits, and you can do things that we talk about later on in terms of rebalancing and splitting to try and balance the workload. However, what this doesn't really fix is the problem that you can very easily have hotspots. And so I think the example they gave in the book is, if you have something like sensor data, and you partition things by time, by date, by time, well, then all the activity is going to be on the most recent partition, so you could wind up with this thing where, no matter what you do, the most current day is getting all the writes and it's getting 80% of the reads. And so that just won't work for that type of a use case. So then the other alternative you can do is you can hash the keys, and there's various hashing algorithms. And so the idea is that effectively, as close as possible, the hash function is going to create a uniform distribution of hash values. And so then you know that, okay, it's going to be pretty much fairly split across the different partitions. So the downside of that is that now, if you're trying to do a range query, the hash function is basically going to just scatter. So if you do, last names between Smith and Thomas, then basically they're going to get scattered everywhere. So the load will be even, but now they're just all over the place. And I thought this was kind of an interesting thing, where the author talked about, in Cassandra, you have compound keys. And so if I forget the example they gave in the book, but it's sort of like, if you hash the sensor ID, but the second key is date time, then essentially, yes, the sensors will be evenly split across all the partitions, but within a given sensor ID, you can have all the data sorted by date and time. And so then it's very easy to do a range query within a given sensor. And if you want X many sensors, then most likely those X many sensors are all going to be spread out amongst the different partitions. All right, so that's sort of the opening in terms of partitioning. So the first question is just how do you split things up between partitions? So any comments or questions? I forgot to ask at the beginning just if there were particular questions or topics people wanted to hit today. So just pause here. All right, well, feel free to jump in at any point. I'll just keep moving on. So as I said, the nice thing about hashing is that it will tend to create a uniform distribution, but that's still no guarantee that you won't have hotspots. So, imagine if you're Twitter or something like that, you can evenly spread all of the accounts across multiple partitions. But if you have certain users who just have millions and millions of followers, and then if there's some event, so if that celebrity has a concert or they're in the news for something good because they're getting married, or something bad because the police, then you can just have this burst of activity all associated with this one user. Nothing you can do about that. That's still going to create very imbalanced workload across your partitions. So generally speaking, none of the commercial products at the time of the writing of this book have any type of automated solution for this. And then there's some things you can do. You can try and augment the key with some sort of random value, and then that will spread things out. So then your celebrity's gonna basically have sub keys that are spread across the different partitions. But this is not something you would want to apply universally to every user. So it's still kind of this awkward thing where you would have to sort of manually decide who are your special case high volume users that you want to treat this extra way. All right, so that's how you deal with your primary key and how you do partitioning. So the next thing is secondary keys. So this is different from the compound keys. So if you're saying, okay, I have a database of cars, and if someone wants to buy a used car, I have whatever, let's say make as my primary key, but let's say somebody wants to do a search by color. Well, how are we going to handle that? So you can have another index for color, and there's two common ways that you're going to store this secondary index if you at all even allow it. I thought about doing a little lookup just to see today if there are any of the big companies that I didn't get around to, I'm sorry, but just to see if there are key value stores that today still don't even support secondary indexes. It's a non-trivial thing to support it. It's just fundamentally that NoSQL key value paradigm doesn't really line up with secondary indexes. So of the two ways to do it, one way is you have this local index, right? And so the idea is that on each partition, you keep track of, in this case, I said color of the cars. You keep track of color of all of the data that's on your partition. And all the other partitions have to keep track themselves as well. And so you're going to have red cars, black cars, white cars, and every other partition is going to have red cars, black cars, white cars. So if somebody wants to do a query and they say, I want red cars, then basically they're going to have to go to every partition and say, tell me about your red cars, and then get back data results from all of them and then merge those results together. So that's what they call scatter gather. So if that's the case, then why would you want to do this if it sort of creates that extra? It's a lot of traffic. It's also just like conceptual work that needs to be done to do the scatter gather. Well, the reason is because writes are very simple. So if you insert a new car, then even if you had 10 secondary indexes based on whatever, color, type of engine, this, that. All those secondary indexes are local to your partition. No biggie. So that's why this local index architecture kind of makes sense. So the other thing you could do is, instead of doing that, you could just say, no, we're not going to spread out the index all over the place. Instead, what we're going to do is we're going to have a global index. We're just going to have one index for color. The thing that I thought was kind of interesting about this, at first I was like, oh, but after thinking about it a little bit, I realized that this global index is actually still spread out across all the different partitions. If you didn't do that, you'd have hotspots. But the idea is that for a particular key or a particular range, so if you say red cars, then red is probably located only on one partition. So as long as you're accessing the secondary index that way. And so if you had a secondary index that was date, I guess there's a possibility, if you wanted a date range, you said last week, that maybe, part of last week is on one partition, the second half of that range, it lives on another partition. So maybe you end up hitting two partitions, but at least most likely you're hitting, one, maybe two, but not all the partitions, not like scatter gather. The cool thing about doing reads with this global type of secondary index is, again, that you're only hitting one or two partitions. The downside for this, however, is writes. So imagine a scenario where you do an insert of a new car in this database and you actually did have a dozen different secondary indexes. Well, just randomly speaking, those secondary indexes are going to be on different partitions. And so just to insert one row, you wind up then having to push all this stuff out to all these other partitions to say, hey, update your secondary index, insert this new value for this car that's red, insert this new value for this car that's this type of engine. And in particular, the danger with this is that you can really slow down the response time to the user if you require all of these secondary indexes to be updated synchronously before you return success to the user. So there's the note. For this reason, this is why you usually do asynchronous behind the scenes updates. And that's all well and good for normal operations, but then it does create a bunch of failure modes that if something fails between the time when the initial row was inserted and when all the secondary indexes are updated, then what do you do? So that can be a bit of a challenge. All right, so let me just pause here. So that's the main content about how do we create partitions, how do we store them, how do we store information on them. The next topics are going to be about how do you keep things balanced. So any comments or questions? All right.
What happens if, what happens if hotspots are not in the same place? If they wander around? I mean, at first, one piece of information is hotspot and in a few days it is another.
Basically, what the author said is that if you have a hotspot like Twitter, you have some really popular person, then at the application level, you kind of need to special case this, that there is no generic database solution to solve for that.
Mm-hmm.
That's all I got.
I have a quick question. So about the last item, about write to the global second index. So you said writes are more complex because other partitions may need to be updated for each. So for example, we are inserting a new item. Let's take the car as example. We are inserting a new car into the database. In this case, say it's a red colored car. So we need to go to the color secondary index. And then it will be only involved one partition. We assume like all the red color that secondary index is in one partition. So we just go ahead, go to that partition and update it.
Yeah, that's right. So imagine that your primary key is on make, okay? And so you say, okay, I'm inserting a row for a Toyota. And so that's on, let's say you have whatever, 9 partitions. And so Toyota is on partition 8. So then if I have a dozen secondary indexes, so then I'm gonna insert a row into the red index because it's a red Toyota. Well, if I'm lucky, red might happen to be on partition 8, but maybe it's on partition 7. Okay, and then I have a secondary index on the type of engine. So this car has a V6. Well, maybe that's on partition. So the engine type index is spread out across all 9 partitions, but the key V6, maybe that's on partition 4, right? And then if I really have a dozen secondary indexes, I don't even know what a dozen features for cars are, but like style of car, how big it is, whatever, I don't know. For each of these dozen indexes, whatever your particular value is, I'm an SUV, I have, 4-wheel drive, I have X many cup holders, whatever those indexes are, you're gonna have a particular value, and so you're gonna have to insert into the place where it's storing, that thing. And so just statistically, randomly, if you have a bunch of these, odds are that they're just gonna wind up on a bunch of different servers.
So can I consider the main differences, like say we have a global secondary index, like we have 3 secondary index. And then when I insert one item, I need to, seems like there are 4 writes there, at least. Like one write is to go insert item for the primary key case, and then we need 3 other writes for updating the other 3 secondary index in terms of, and then compares with the first, compared with the key range partitioning. All those things we can just finish in one partition, like we insert that to that partition, and then in the same partition we will update all the secondary index, which is the local secondary index.
That's right. You're always doing 4 writes. So if you insert a row, you always have to insert into the primary key, and you have to insert separately into each secondary index. With local indexes, you guarantee that all 4 of those inserts are happening on the same server.
Yeah.
Okay.
Thank you.
But reads get complicated. But when you do this global index, then you incur this potential, not even potential, but like the likely scenario is that your secondary index writes are going to be on other partitions. And the whole point of this architecture, right, is to scale this. And so you cannot guarantee fast response as soon as you're trying to do a write to another server.
Okay, thank you.
Yeah, thanks.
Do anyone know like how Spark data is partitioned by default? Because most of the time I just partition by the column I specify, but then I'm just curious if they're run, like what is under the hood if I don't specify a partition.
So Spark initially was created with Hadoop.
Right.
Now it supports lots and lots of different data stores behind the scenes. But when you talk about partitioning in Spark, generally speaking, like, Spark is going to, let's see here. So map reduce, this is actually stuff that's covered, like I think in like chapter 12 on batch processing or something like that. But so map reduce, the idea is you ship the computation to where the data is. Okay, so you spread out the data on a Hadoop cluster, and if you say all my cars are split out by, let's just for simplicity, by make, then you simply say, if I need to count the number of cars, then I tell the node that has the Toyotas, count how many Toyotas, and I tell the node that has the Ford, count how many Fords. And then I can just take all those sums, and if I know mathematically, if I add those together, then I'll get the grand total sum, right? So that's the map reduce paradigm. So Spark isn't about pushing the computation to where the data is. Spark is more about, I have an optimizer, I know where the data is, I'm going to do various calculations, and when necessary, I will actually move data from one node to another node to do a different kind of computation. So the partitioning is really there about being very aware of physically where the data is. In this case, we're not worried about sort of a transactional database. You know what I mean? So this isn't like, generally not, the use case for Spark isn't that I have this database of used cars and now somebody added a new used car and so I'm going to do an insert into this data. So generally speaking, your Spark data is going to be sort of like this is not 100% accurate, but it's you know, it's going to be sort of an offline data warehouse replica of your live transactional data.
So it's already based on like how your data is stored, and then just take that as partition.
Yeah, and depending on the nature of your calculation, you can choose, you can say my online transactional database might store things this particular way, but I'm going to incur the costs to re-spread it out and partition it this other way, right? So, so my live database may be partitioned by make, but I'm going to actually store the data in my Spark cluster by date. Because I know the types of calculations I'm doing, it is much more efficient to keep all the cars by date together. And that's my very minimal, I don't do a lot of Spark stuff, but that's my very minimal understanding of how people manually tune and optimize their Spark calculations, is that they, Spark itself has an optimizer, but it won't, for the most part, it won't do super aggressive data moves. It'll shuffle data around as it needs for the computations. But you can say, before I even start the computation, move everything around so it's sorted by date. Do this whole series of steps, and now I'm going to do some other calculations. So reshuffle all this data and now sort it by, you know, by engine size. And I know that that will, in the end, cause the rest of these computations to be more efficient. So that's where people are hand tuning their data flows by sort of manually inserting these massive, expensive data moves, but just because they know that that's gonna reduce the moves that Spark has to do later on. Does that make sense?
Yeah, because I asked this question because like on my job, I have to like help refining the Spark data pipeline. So like understanding how partition works, or how to make the query more efficient, really helps. Like sometimes you create way too many partitions, and like the storage becomes very inefficient, or the calculation becomes very inefficient, and then it breaks down. So that's why like what you said, like the manual repartitioning prior to a certain calculation really makes a difference.
Yeah. If your order data is sorted by date, and you're going to do a bazillion calculations per customer, you probably end up winning in the long run by doing this super expensive repartitioning by customer at the beginning, right? That's very costly. But then all these other calculations run much faster, because you know it's able to keep the data very local for the rest of the computations.
Yeah, sometimes like if you have uneven partitions, and then the calculation only happens in certain partition, but the other ones are not used, then your job might break too. So there are many ways that it can break. Yeah,
I forget what that's called, but where you have like the one slowest node and everybody's waiting for it, right? So
exactly.
So if all your calculations happening on 2 nodes, even though you have a 64 node cluster, 62 of them are just sitting there like, I don't have data for what you care about. It's all over there. Yeah, and that's the kind of thing that the Spark optimizer doesn't really know how to solve for the most part, right? You're more manually detecting these bottlenecks and saying, oh, if I actually spread that data out over all 60 nodes, then I could get them. Obviously, there's a one-time cost you pay, but if it helps enough, then you get bang for your buck. So I haven't read ahead far enough, but I do know that the batch processing chapter, like half of it's on MapReduce, and that it does talk about Spark a little bit.
Awesome. Sounds great.
Okay, cool. Well, thanks for asking questions. I feel much better when it's more of a conversation. Otherwise, I don't know if I'm just boring you guys or whatever. Okay, so we talked about how we locate the data and how we locate secondary indexes if they're supported. So the next thing is, as much as you do this, ultimately you're going to have to do rebalancing. So you can do rebalancing for two reasons. You can do long-term rebalancing for two reasons. One is because you discover that the data is skewed. You know, you divided it up a certain way, but ultimately, you know, even though like you looked at the dictionary and you decided to split the alphabet by whatever, for some reason, everybody with the letter A is signing up for your service and nobody with the letter T is signing up for your service. And so the A partition is just overloaded. So now you got to split it out. The other way in which it'll happen is, good news, your company's taking off and you just have more and more customers. So even though your partitions are perfectly uniformly spread, we're going to go from 5 partitions to 9 partitions because the company's growing. So we just need to be able to take it and spread it over more nodes. So those are like the long-term reasons why you do it. Short-term also, you just have a node failure and other ones are picking up the workload, that sort of a thing. So it mentions, typically the way rebalancing is thought about, while the rebalancing is happening, you're still supporting activity. So it's not like you shut the whole system down and rebalance. So you have to consider that. You ideally, again, want to spread everything evenly. And then, of course, the goal is to minimize the amount of data that you're moving. So they give an example of if you hash things and you just take this resulting number and you do, you know, modulo the number of nodes you have. Rebalancing for this would be really terrible because if you do some number, you know, modulo 5, and then you change it to 7 nodes and you do these hash numbers modulo 7, then basically huge amounts of your data are going to have to move from one partition to the new partition where they're supposed to be. So you're not going to handle it something like that, even though mathematically that's very simple. That's going to result in lots of movement. So they come up with other schemes for how to do it. So one thing, if you think about it, that's relatively easy is if you have 7 nodes, you don't have to have 7 partitions. You could have 1,000 partitions and put roughly 140 of them on each of the servers. And so then if you want to go to 9 partitions, then basically like each one can like give up 30 partitions. So then they're down to 110 on each server. And then the new servers, you know, they pick up partitions from all the other guys. And then they also have about 110. So that's a pretty, you know, straightforward way of doing things. And unless your company just grows like crazy, you know, if you start with 1,000 partitions, then 1,000 of these little mini partitions, then no matter how many actual servers you have, if you have 3, 5, 9, 11, you know, you'll be able to distribute them fairly evenly across the different servers. And then they talk about this clever thing that you can do is that in reality, as you add servers to your system, maybe the new servers are faster than your old servers. So maybe you actually want to purposefully give them an uneven number. So say, oh, the new servers, they can handle 20% more, you know, than the old ones or something like that. So that's kind of a clever thing you can do. So fixed partitions works well for most use cases, but if you really are unsure, another thing you can do is you can do dynamic partitioning, where basically partitions can either be split or merged. Excuse me one sec. I had a sneeze there, but it didn't come out. So if you merge and split partitions, if you support both those functions, then the database can grow or shrink infinitely, and basically your bases are covered. So basically the typical way this is implemented, you have a size range. And so basically, let's say your size range is 10 to 20 gigabytes, okay? When it exceeds 20 gigabytes, you split it into two chunks that are about 10 each. And as you keep doing this, if there are more partitions, eventually you can say, okay, I split into two, I'm gonna keep one, and somebody else who has a lighter load is gonna take the other one. So that's a good way where over time, the partitions will spread around, and you'll be able to balance your load, but with fairly minimal data movement. Let's see here, what else is in the notes here? I don't know if all these databases support merging. I mean, usually you worry about databases growing. You don't really worry about databases shrinking. It was mentioned, but not really in much detail. And then this other Cassandra use case I thought was kind of interesting. So they do partitioning proportional to the number of nodes. So instead of having these hard-coded sizes like between, at 20 gigabytes, we split it into two. They just simply say, we're gonna have, 5 partitions per server. And so then these partitions will, over time, keep getting bigger and bigger and bigger. But the kind of cool thing is that real world companies, as they grow, what they will tend to do is increase the number of servers. And so because of that, then if your size doubles, but you go from 3 to 5 partitions, then effectively you've kind of doubled the number of servers approximately. And so then now your partition size comes back down to sort of the original size again. So it's a little bit different algorithm with I think the intent being still that you're going to have a relatively stable partition size. So those are 3 different approaches, just sort of having a fixed hard-coded number of partitions, expecting that you have enough that you can just spread them out evenly amongst your different servers. You can split them, or you can use this clever thing of a fixed number per the number of servers you have. All right, and then the last thing on rebalancing I thought was kind of interesting is you could do it in a fully automated way where the system just says, whoa, look, this partition is really big. It's 22 gig. We said 20 was a limit. I'm going to split it. I'm going to move half of it onto this other server that has lighter load. But if, say, your Twitter, Facebook, something, and let's say 8 p.m. is the busiest time of the day when there's the most activity, if your system automatically detects that at 8 p.m., it's going to suddenly be doing this split, and it's going to be trying to copy this data from one partition to another right in the middle of your peak time. So maybe what you want is a system that's semi-automated, where it detects the problem, it alerts the operator and says, hey, this partition is getting really big, maybe we want to split it to try and balance the workload. And then the operator can decide, it's 8 p.m., I'm not going to press go, I'm actually going to wait a few hours, then when it's not our peak busy time, then I'm going to say, okay, go ahead and do it now. And then I thought there's an interesting race case here that they mention where if you have a node that's slow and your system detects a failure, then what it needs to do is it needs to start offloading data onto the other nodes. And if that causes if you have rebalancing that then kicks off on top of that, you can kind of get into this race condition where it's just piling on more and more load for these background processes that has absolutely nothing to do with your users. And so again, you may want to insert a human into the middle to sort of say, does this make sense? Should I say yes, go ahead and rebalance? If you have a 24-hour operations like a big company like Twitter, then it seems pretty reasonable that you would insert that. If you're a small company, you know, maybe you don't have that kind of resources. But if you're a small company and it's 8 hours before the operator shows up to say, oh, look, there's a warning message saying the partitions want to be rebalanced. I mean, can you tolerate, you know, 8 hours? Maybe. So anyway, so that's the last thing on rebalancing. All right, so then the last topic has to do with request routing, and this is a partial discussion. So some of this stuff I think we're gonna revisit some of these concepts in later chapters. But the main thing is that since we're saying that nodes can be moved around, rebalance, split, then you have this service discovery problem. Somebody needs to keep track of, somehow people need to know, if I'm looking for Toyotas, where do I send my request? What IP address do I send my request for Toyotas? So you can say that the clients are gonna send a request to a node, and if it's the wrong node, that node will forward it on. Or you can say, I'm gonna add a new layer, I'm gonna have an intermediate tier that's just the request processing tier. And so the request is, oh, you want a query for Toyotas? I'll send that to node 4. Or somehow you can say that in my application, it's a custom application. I can keep track of things there and I'll just tell the clients. It doesn't matter. In any one of these 3 scenarios, still there is a particular computer, whether it's the individual nodes, whether it's this new routing tier, or whether it's the clients, somebody has to actually keep track of this list. So it doesn't matter which of those you use, you still have to have some way of saying, I'm gonna update that list that says Toyota's on node 4. Oh wait, now Toyota got moved to node 5. And so there's consensus is one of the general algorithms you can use. So that's tricky. That's going to be talked about in chapter 9. Last week we mentioned a little bit. So a lot of people use Zookeeper. So Zookeeper came up last week. And then another way that you can do it is using what they call a gossip protocol. And I'm not quite sure. I read a little bit about gossip protocols. I'm not really quite sure. So I mean, gossip protocols, basically, it's like the nodes just sort of talk to each other and they say, hey, by the way, I moved Toyotas from node 4 to node 5. But what I don't know, and I don't know if anybody here knows, what do you do in the case where somebody requests Toyota before the notification actually went out? You know, in that small window of time before the gossip message went out. And my guess is that it may be just application specific, but you know, it could either be the case that when you do that, you just you fail the read request. You know, it could be that forces at that point you to send some gossip messages. Oh, you're not quite up to date. Toyota got moved over to node 5. I'm not quite sure how it works, but basically the idea is that Zookeeper is the idea of a central authority, and the gossip protocol is the idea of just distributed. You're sending out information, you're sending out updates. Much like last week, somebody was talking about the gateway updates. So there's no way you can have central updates for the internet. And so you have to have something that's more like gossip protocol, where basically you have these gateway update protocols where they're just sort of sending out messages, and you know that there's going to be a latency before these messages sort of percolate their way, you know, all the way around. All right, any questions about request routing? I know there's still, to me, this was sort of like introducing the question, but not really answering it completely in the book.
I have a quick question. So I know one concern. I have heard of one consensus protocol called Paxos, I think. Is that one kind of gossip protocol?
I think consensus, I'm not familiar with it. I don't know a lot about consensus. I'll learn more when we read chapter 9, but I'm pretty sure that consensus is different than gossip protocol. So consensus means right now, let's all of the nodes talk to each other and agree on some answer to some question. Okay, so there's different questions you can answer. You can answer, who's the leader right now? Is this node down? Where are Toyotas currently stored? Okay. Gossip protocol is not a synchronous, we're going to decide this now. It's just sort of like, hey, by the way, node 2, I moved Toyotas from node 4 to 5. Hey, by the way, node 1, I moved Toyotas from node 4 to node 5. And depending on the protocol, it can either be kind of a star scheme where you tell everybody, or it can be one where it's like, I tell node 2, and then node 2 tells node 1, and it just sort of spreads. So I think generally gossip protocol is more of the latter. Instead of you telling everyone, it's you tell a certain number of people, and then they tell a certain number of people, and it just sort of spreads. So the way I think of it is that you wouldn't pass every update independently. You're sort of collecting a bunch of updates. And so when node 2 tells node 1, he's like, node 2 is going to say, oh, I heard this from node 4, Toyota moved over here. And I also heard this thing from node 3 that Ford's moved over there. And then there was this other thing that I heard that, Ferraris, they also got moved from node 3 to node 5. Does that answer your question?
Yeah, thanks.
Okay. There was a final little section about parallel execution. And so sort of talking about the difference between, we talked about ranges a little bit, mostly, we think of this as like pulling a single key. But so if you have an analytic use case, so this would be like typically, Spark runs, things like that, then you're going to want to pull things from multiple nodes in parallel. And so this is where Spark, for example, has an optimizer that coordinates this. And so I guess chapter 10 is the batch processing chapter. So they're going to talk about that. So even though we have these partitions, we have things spread out, we don't necessarily have the technology to really take advantage of them very well. We're just trying to, what this chapter mostly has just covered is the scalability stuff. So if you have Facebook users and they're just looking for their news feed, you've now successfully spread out that workload over multiple servers so that the server just doesn't get overloaded and crash. All right, any other comments, questions?
I have a sort of hypothetical scenario. So imagine a scenario that you have 100 servers potentially, and you have not that much data. I would assume splitting things into a bunch of partitions and throwing it across many different servers is probably going to just add extra overhead you don't need. Do you think there's any way for it to automatically detect that and kind of say, okay, we have 100 servers available, but let's only put partitions on 5 of them because that's all we need at this point?
I don't know these this product space really well, but I think that if you used dynamic partitioning, okay, where you say 20 gigabytes, I'm going to split it into 2 10 gig halves, and below 10 or maybe below 5 gigabytes, I'm going to merge 2 subsets. Then maybe some constraints, because you don't necessarily want it to merge everything down to 1 partition, but there may be some sort of minimum number. So if your product supports merging and you're worried about this use case, I think what you could do is you turn on merging. And then I don't think the system will shut down your nodes. But if you look and you see that merging has happened and I'm actually only using 7 of my 100 nodes, then you could, as an administrator, you could say, I'm going to change a parameter, max nodes is now 20, and then you can shut down 80 of the nodes and stop paying for them.
Mm-hmm. Yeah.
But off the top of my head, again, I don't know these products really well, but I don't think that like Cassandra or anybody's going to actually do that for you, but you can at least say, oh, okay, I have this cushion, whatever, you know.
Do you have any idea about sort of the scaling of that whole scatter gather process? Like if you start spreading that across more and more systems, I assume that would potentially slow things down over time, potentially. If you're saying I need to gather information from many different systems, I don't know, it wouldn't necessarily be linear because you're kind of just waiting for the slowest link potentially, but
I think it's complicated. So obviously if you have 3 partitions, 5 partitions, right? Scatter gather is not that scary. But where I think it gets really complicated is that a lot of systems don't really let you do queries on secondary indexes. So a lot of people spend time designing their systems so that you don't. So you know, like for Facebook, I don't know that you really are hitting secondary indexes, right? Like they want you to go to your news feed, but they don't really let you do searches. You can't really just go to Facebook and say, I want to do a search on inauguration, right? So that's one of the reasons why they don't have that feature is I think because it's just extremely difficult to support that in their database. So this chapter does talk about that use case, except real world products, I don't know that they often, for like massively large products, I don't know that they actually support that.
Yeah, they might just avoid it.
Yeah, and then at the other extreme, if you know you're doing a big analytic thing, then you might not be using your Cassandra database, you might actually be using Spark or something else where you're not running on your production Cassandra, you're now shipping, let's say, a snapshot as of last night, and then you're running like some giant recommendation engine or whatever, some algorithm, you know, but it's not on like the live instantaneous production database, it's just something. And so then you can obviously choose to organize it and index it and do things with that data.
Yeah.
But it's always difficult to support secondary indexes. I think that's why, in my opinion, and I may be a little biased because I am a relational database guy, like that's what I know best, but I think that's one reason why they'll never go away is because secondary indexes are supported really well in relational databases. And so if you don't hit that, you know, Twitter, Facebook, Amazon type scale where you just fundamentally cannot build a giant enough Oracle or whatever database, then okay, maybe it's not perfect, but the good news is it just supports all these workloads and it's super mature. The servers have really good stability and uptime. I don't worry about corruption. I don't worry about this, you know?
Yeah.
And so that's why I think, you know, you're not going to support Facebook with that, but for departments within Facebook, they may actually have relational databases where they run things. You know, and then if you are lucky enough to have a Spark cluster, then I guess even if it requires shuffles, you the benefit you get from having 32 nodes in your cluster, right? From a response time, it can outweigh even though you're doing it inefficiently. So something that a relational database may have a clever way of doing it, even if you have to brute force it and scan through all the data, the fact that you spread it over 32 workers in parallel, maybe no biggie. It's reasonable. And so if you're fortunate enough to have that, then you can kind of right? You don't have to have the most efficient workflow. If it's just, hey, here's a tool, I have Spark, I have a team, they know how to use it. Even if theoretically this one query would run faster on a relational database, just get it done.
Yeah.
Anybody else? Any other comments or questions? All right, so just to kind of wrap up, so I thought that this chapter was, in some ways, one of our lighter chapters. It doesn't have that many heavy problems that it introduced, but at the same time, it's sort of like, and this question will be answered in chapters 8 and 9, and this thing we'll discuss more, how to do analytic workloads and parallel execution. We'll talk about in chapter 10 in the batch processing. So in some ways, it's sort of like, if you write a book, you have to divide it into chapters. And so this chapter just happens to be sort of like introducing certain things which get talked about more later.
I second this.
All right, well, if there's no further questions, I don't know, Ryan, scheduled the project thing for 1:30, so we actually have a few minutes. We could just chat. I was talking about actually just for fun looking at that geo thing.
Yeah, I
transition early.
I ran into this problem that site only lets you play one game per day for free. And so I could pay for it, but I don't know, not really.
Or you could send me the link, and I don't know, do I have to sign up? I have to like create an account?
I think you have to create an account.
Okay.
Yeah. But
all right, probably not worth the hassle.
Just filling everyone else in. I was mentioning this game earlier called GeoGuessr, where you get plopped random places in the world on Google Maps, and then you have to just look around and you have to figure out where you are just by looking at the landmarks and the buildings and the people and all of that stuff. And they blur out the obvious stuff, like you can't just look at license plates and stuff like that, but you just have to locate yourself just by your surroundings. And it's a pretty interesting game, and I figured since we have a somewhat international group here, it might be interesting to see.
What's the name again?
GeoGuessr. I can put a link in here.
Sure. Great.
Wasn't there a competition somewhere in Chicago that you're supposed to do some kind of, was it landmark detection or, I don't know, related to this, that you're showing some random pictures and you're supposed to find out where in the world you are?
Yeah. I think that one's kind of limited to more famous things, but it's definitely related. This one, it plops you a random spot, and then you just kind of click around and you're trying to walk around until you find the spot.
I'm curious how well I can do within the United States, but I don't think I would do very well around the world.
It's actually kind of surprising, because typically you can wander around and you can find a flag or something like that, or you can look at a restaurant or something and they'll say like such and such restaurant.be, and then you know that it's from Belarus or Belgium or something.
Okay.
So it's one thing to like end up in the right country. It's another thing to be like, this is this specific street that I'm on. And some people are good enough that they're able to locate and navigate very accurately like that.
That's cool. I think if it plopped me someplace that doesn't use an alphabet, then I think I'm hosed.
The real difficult ones are the ones where it puts you on a random dirt road and all you see around you is fields, and then you just have absolutely no way of finding any discernible information other than just the crops around you.
Mm. I was looking at a talk and they showed an example of Sinhalese, which I guess they speak in Sri Lanka. And I mean, you could have a million signs that says, you know, this is the blah blah restaurant located at this address in this city in the capital of Sri Lanka, and it would do me absolutely no good.
Yeah, yeah.
I can't remember, last week, did we talk about that that OpenAI Dolly model, the blog posting about that?
I don't think we discussed it. I know it got posted, I think.
Yeah, you posted something, I think, on our Slack, but that was just really cool. So for people who haven't seen it, their latest thing that they've done, they of course have GPT-2, GPT-3. So they did Clip, where they used text captions for photos on the internet as a training set. And so then they used a GPT-2 style architecture for the text, and they used standard vision type architecture for the images, and they used contrastive loss to train basically these two networks. They trained the text and the image to have a shared internal representation between the two of them. And then they could basically say something along the lines of, here's a test image from ImageNet. ImageNet has 1,000 classes, and so I'm going to create 1,000 text strings that's like a photo of a dog, a photo of a cat, a photo of an avocado. And then basically, you know, the model would say which of those it thought was the best. And so then it would say, oh, I think dog is the closest, so I'm going to guess this is a dog. So then the latest one is Dolly, which is a play on the Disney movie WALL-E and the artist Salvador Dali. So then what they did is they had the image part be a generator instead of just being an encoder. And so now they can say, the one that's like the top of their example, which is just fantastic, you know, I don't know exactly what the wording was, but you know, a chair that looks like an avocado. And it was I thought it was just pretty freaking amazing that it's like, oh, look, here's a chair that's avocado shaped and it's green. Here's a chair that's like avocado shaped green, and the cushion is like a round light brown cushion right where the pit of the avocado would be. And, you know, just stuff like that. So they're writing up a full paper on it. It hasn't come out yet. There's just the blog post that Ryan linked. And then they did show a few things that they said this model isn't good at. You know, it's not perfect at counting objects and things like that. And it asked for something weird. It asked for a pentagonal clock, only 5 sides. And so some of the images it created had 6, you know. But just some of the images, you know, and like the second one here, you know, a storefront that has the word OpenAI. It's like, wow, it's generating photorealistic things with like different fonts, different style. It could be, you know, something written on glass. It could be physical letters that have 3-dimensionality, and then just arbitrary things that it couldn't possibly have seen in the training set. You know, what if a, you know, porcupine were a cube? So There's a lot of really cool images. Oh yeah, here's one. A collection of glasses is sitting on a table. I thought it was interesting because I read that and I immediately thought like wine glasses, water glasses. And then like there were pictures that had eyeglasses, and some of them had actual eyeglasses and wine glasses mixed. It's like, oh, yeah, I guess it was ambiguous. It's not surprising that it did that, but it's pretty insane that it's generating such photorealistic stuff and such potential variety. You know, it's not like they're all cartoony or they're all this, or, you know. So I think within a few weeks we'll have the full paper. But there's a lot of stuff they already did playing with this that was just really cool.
Sorry, hi Dad and Ryan. haven't kind of spoken for a while. Hey guys, I just wonder. I haven't had a chance to look at this, but it does sound very cool. But did you say that it's actually generating the images, not really identifying the images?
So I had mentioned this clip project. That was a very, very different way of training something to be able to classify images. So is this a dog, is this a cat, or whatever? The DALL-E project, they completed at roughly the same time. That's the link that Ryan put in the chat. That's a generator. So just like GPT-2 and GPT-3 generate text, now DALL-E is generating images.
Gotcha.
And so if you click that link and you look, those are completely 100% synthetic images that it generated just from a text prompt after it had been fully trained.
Gotcha.
And so you'll see if you like expand it that they can show you like the top 100 images it generated for a chair that looks like an avocado. And some of them are better and some of them are worse, but it, you know, it's just kind of amazing. And this is sort of zero-shot performance. So it had all of this training on images and text, but it had no warning of what you were going to ask it to do. So when they said a chair that looks like an avocado, it had no warning. There was no specific training about chairs or training about avocados or whatever, right? It said, you know, a porcupine, that's a cube. It had no way of knowing that you might ask for something like that. Going into the details, it's just like the text models, it's generative. So it's actually kind of doing things sequential. So it starts in the upper left corner and then it goes like across. And then it goes back to the next row and goes across. It goes like that. And so they can feed it, if they want, a certain amount of the image starting from the upper left. So one thing they can do is they give it the top half and say, just fill out what the bottom half of this image looks like. Right. And so then this one thing they did was, I think they said it was a statue of the Greek guy Archimedes. And they gave him a hat, but they only showed you the top few pixels of the hat. And then basically what they did was they asked it to do this task over and over again, but each time they rotated the hat like 5 degrees. And in doing so, it then rendered Archimedes facing 5 degrees, slightly different directions. And so they said they were able to composite that into a 3D, basically, rendering of Archimedes.
I wonder what this will do to the whole kind of like photography or artwork world that's still making their money off, I mean, the original art and creation.
Yeah. Yeah, theoretically, if you need clip art instead of, right, finding stock photos, you could just say, hey, Dolly, give me a whatever, baseball player about to catch a ball.
Yeah, yeah. And all the PowerPoints that people do that need photos, that would, yeah.
Yeah. Right, like Maya said, you can say, I want a daikon and a tutu. Like, you know, doesn't have to be out there. I can't remember where I saw it. I saw something about artists who were using GANs to create new kinds of artwork. So the cool thing is, as soon as you have this capability, right, then an artist can add another layer that the computer can't do. And so then they can make like beautiful things where like maybe, you know, the GAN can do something or this Dolly can do something, but then the artist can figure out a way to use that as like a starting point, and then, you know, have it be a stamp or have it be something, and then they do an artistic interpretation beyond that, you know. They can take like a computer that generates 1,000 images of a chair that looks like an avocado, and they can then make a mosaic as an artist of those images into like a big, you know. So the cool thing is that I don't think artists will ever be out of a job.
Well, the thing is that the machine will continue to learn on top of that, right?
Yeah.
So like, the artist will have to be, will continue to be super creative on that.
Yeah, I mean, I know very little about art, but at some point, painters got pretty good at making realistic portraits, right? So then the art world evolved into non-realistic things, Impressionism, and then ultimately Cubism and whatever, right? So yeah, so when the computer can do, you know, a daikon and a tutu, then an artist may just then be able to do some level beyond that. And when the computer can do that, then the artist will just move on, you know. I think there'll always be a need for artists to just sort of think of what's the next level of interesting thing you can do. Yeah, but to your original point, so I think the artists are safe, or at least the top artists are safe. Yeah. But yeah, stock photos, I don't know that they could go out of business.
Cool.